We're going to be looking at Chapter 10, which are counting methods. Some of the different sections in Chapter 10 are counting by systematic listing, fundamental counting principles, permutations and combinations, and then problems that involve not or the symbol or. So today we're going to be talking about counting by systematic listing. So there are different types of problems that we can have here. We can have the one-part task, which means there's just one part to the outcome. Or we can have two-part tasks, which means there's two parts, two different things could occur, or multiple parts, or other different listing methods. So one-part tasks are examples where there's only one result. For flipping a coin, you can either get heads or tails. You can't get both. When you roll a die, you can get the number 1, 2, 3, 4, 5, or 6. You cannot get more than one number unless you have multiple die. If you think about electing the president for your club, there can only be one person that is elected president out of the club. If you wanted to elect the president and the vice president, then the same person can't be in both offices. So there would be two different people. That would be a two-part task. So another example here we have again is selecting a club president. If there are 4 people in the club, then the set is the set of students or set of people, M, A, T, and H, representing the people's names. How many different ways can this group select a president? Well, Mike can be the president, or Adam, or Ted, or Helen, but they cannot all be president at one time. So there are 4 different ways that this group can select a president. So how many 2-digit numbers can we form from the numbers 2, 4, and 6? Well, in this case, we're looking for 2 possible results. I could have the 2 and the 4 listed together, or the 2 and the 6 listed together, or I could have the 4 and the 6 listed together. Now, there's no mention in this problem that you cannot duplicate elements. So if I come up with a table and I choose the first element and then the second element, my table would consist of, for example, the numbers 2, 2, 2, 4, 2, 6. So it's almost like a multiplication table if you remember back to doing those. So for example, here's what we would have. Element 2 paired with element 2, element 2 paired with element 4, element 2 paired with element 6. Or I could have 4 and 2, 4 and 4, 4 and 6. So basically I'm taking the first digit and I'm pairing it with all the possible digits, and then I take the second digit and pair it with all the possible digits. Now in this case again, I'm not worried about duplications. So the set 2, 2 and the set 2, 4, I can also have the set 4, 2. So in this case, we're not worried about duplicating or having the same 2 elements in the set. So here's all the sets of possible numbers if I roll 2 die. So I could have a red die that's the numbers 1 through 6, and the green die. So all the possible combinations would be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Or I could have 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, or 4, 6. So there are a number of different possibilities. Now this is very important. This chart of the die possibilities is very important when we start getting into more probability information. So you might want to flag this page and keep a reminder to yourself. So find the number of ways Club N can elect a president and a secretary. So remember the club was comprised of the students M, A, T, and H. So if I wanted to come up with all the possibilities for the president and the secretary, then I could have M be president and A be secretary, or I could have M be president and T be secretary, or M could be president and H could be secretary. So again, what I'm doing is I'm taking the element M and I'm pairing it up with all the other possibilities. Now the only thing you have to keep in mind here is that the president cannot also be the secretary. So if you'll notice on this chart, the middle diagonal is blank because you can't have M be the president and M be the secretary. So in this case, you'll notice that we have all the possibilities. Now there is a difference between MA and AM. MA is telling me that M is the president and A is the secretary. But AM is saying that A is the president, but M is the secretary. So how many ways can we appoint this with two members, or how many ways can we appoint, excuse me, I'm going to go back. So how many different ways can we have a person be secretary and a person be president? There are 12 different possibilities, and you see those 12 possibilities listed here. So now, what if I just wanted to appoint committees with two members? So I needed two people to be on a committee from the club, and I wanted to figure out how many different possibilities for committees could I have. Well, in this case, if I go back to my chart again, MA, the committee of M and A, is the same as the committee for A and M, because they're the same two people in the committee. So in that situation, MT is the same as TM, AT is the same as TA. So now we've narrowed our 12 possible pairs down to 6. So again, the question is, how many ways can I appoint committees of 2 members? There would only be 6 possibilities. So if a task has more than 2 parts, it's not quite as easy to analyze with a table because you don't really have the ability to do a 3-dimensional table. So another option for helping us to do this is a tree diagram. So let's say I wanted to build numbers from a set of digits. So let's say I had the numbers 2, 4, and 6. And I wanted to figure out how many different possibilities of 3-digit sets could I come up with, or 3-digit numbers could I come up. So for example, I could come up with the number 246. I could come up with the number 426. So there's different possibilities for the different numbers. So if you look at what we have here, so my first possibilities are I could have the number 2, the number 4, or the number 6 for the first digit. If 2 is the first digit, then the second digit could only be 4 or 6. Because here I said repeated digits are not allowed. So that means, for example, I can't have the digit 222 or the digit 242. So if I picked 4 for the second digit, then that means the only possibility for the third digit is 6. So what I end up with is there are 6 unique possibilities for 3-digit numbers that do not have digits repeated if I have the set 2, 4, and 6. So I'm going to minimize this and show you something else. So what I have here is, what if I said I don't care about repeated digits? Well, that means for the number 2, the second digit could be the digit 4, or the digit 2, or the digit 6. And if I had the digit 4, it could have the digits 2, 4, or 6. So what I end up with is that there are 27 possibilities if I do not, or if I allow them to repeat their digits. Okay, but again, on this example that we're looking at here, we're not allowing the digits to be repeated, so there are only 6 possibilities. Okay, so there are also other systematic, there are other systematic approaches to coming up with the possibilities, and sometimes coming up with different methods is a good idea. So here's a good example. I want to know how many different triangles there are in this picture below. So one of the suggestions is that we start with the letter A, for example, and we match it up alphabetically. So we do ABC, ABD, ABE, ABF, okay? And then we have to go through and eliminate which ones of those are not triangles. If there are any that are not triangles, then we throw those out. For example, the combination AED is not a triangle. And then once I do the ABC, ABD, ABE, ABF, then I would go through and I would say AC, and I would go through the possibilities there. I would say ACD, ACE, ACF. Then I would do AD, ADE, ADF. Then I would do AE, and the only possibilities are AED and AEF. So AED we already talked about is not a triangle. So that can be very tedious and very easy to get things confused, and it's also very easy to duplicate examples. So a better example might be to look at this and say, how many triangles do we have in there that have one region? So for example, AEF, let me highlight that. AEF is a triangle, okay, with one region. There's only one area in there. And DEC has only one region. CFB only has one region. AFB only has one region. And EFC only has one region. So what we did is we basically went through and we picked out the parts of the triangle. Oops, sorry. We picked out the parts of the triangle that only have one region, and we used that information to come up with our first set of triangles. Then we look at this shape and we say which sets or which parts of the shape have two regions. So for example, in that example, AEC is a triangle with two regions. Another one with two regions is BCE. Whoops, sorry. So that I could go through and I could set up which one has two regions. And then I said list all the ones that have two regions. Then I would go with three regions, and the ones with three regions would be DEB, and another one with three regions would be ACD. There are no triangles in the shape with four regions, and then the number with five regions would be the big triangle ADB. So I think that in a case like this, it might be easier to think of it that way instead of thinking of it as starting with the letter A and working it that way. So here's another example. How many triangles are there in this figure? So we can look at the points of the star as being some triangles. So ABJ, CDB, DEF, FGH, HIJ are the obvious four triangles. And then we look at the triangles that have two regions, and there are none. So we go now to the ones with three regions, and for example, if we look at AHE, oops, sorry, we have that triangle there that has three regions involved. And then we can look at all the triangles with three regions, and then there are no triangles in the picture with other regions. So we end up with 10 possible triangles out of this shape. So I hope this helps. You need to go ahead and look at section 10.1's homework in My Math Lab, and make sure that you have any questions, you get in touch with me as soon as possible. Good luck.